Dear friends, in this class let us see the important aerodynamic characteristics of an aerofoil. So the main important aerodynamic characteristics of an aerofoil is nothing but CL versus alpha and CL versus CD and lift coefficient versus drag coefficient and a pitching moment versus angle of attack. So in this class we will see about the lift coefficient versus angle of attack. Lift coefficient versus angle of attack is called as CL-alfa curve. It is also called a lift curve, and this also we can call it as a lift coefficient with the angle of attack. So this lift coefficient curve or lift curve, how we are achieving is nothing but based on the flow condition over the aerofoil. When the aerofoil is in the horizontal and it doesn't have any angle of attack, and the flow condition, flow direction also, flow direction as well as the call line are in the same line, then the flow will not have any deviation and the flow will be very smooth over the upper and the lower surface of the aerofoil. But when the angle of attack, when the aerofoil comes under some angle of attack with the flow direction, then the flow over the aerofoil will be slightly changed, but still it won't be distorted, it won't be getting diverted from the lower and upper surface, and it will be following the same aerofoil surfaces. And as the angle of attack increases, what happens? The flow over the upper surface, mainly flow over the upper surface gets disturbed, and it creates reverse flow and wake regions on the especially behind the aerofoil. Here in this region, it creates the reverse flow and wake regions. So because of that, this is the position where our flow is disturbed, and that means the continuity in the flow gets disturbed. So because of that, there will be a breaking point. So that breaking point where the flow gets disturbed and it is becoming unstable, and that point we take it as the stall point. That means stall point. So that point only we just we are going to see, and so based on this flow phenomenon, we are going to see the lift coefficient versus angle of attack curve. So this is nothing but CL and alpha. So from this lift coefficient versus angle of attack curve or lift curve, we are getting 4 important features. What are those features? We will see one by one. So first feature is nothing but zero lift angle of attack. From this curve, we are first feature we are getting zero lift angle of attack. That is nothing but CL equal to 0. So zero lift angle of attack, and the second one we call it as slope. The slope of this curve, slope of CL-alpha curve. And third one is nothing but our where the flow is getting breakage. At that point we call it as stall point. That point we are taking as this stall condition. In the CL-alpha curve, it represents that stall. That means this point is this one. So alpha. So here we say that there are two important points. One is the CL max. So this is nothing but the CL max, this point, and another point is the angle of attack, stalling angle of attack. This is we call it as stalling angle. So we can say CL max, that is, or stall point. And fourth one is the stalling angle. So These are the four important main features we are achieving from this aerofoil curve. And mainly this zero lift angle of attack comes into the pictures whenever we are taking the cambered aerofoil into pictures. For the symmetrical aerofoil, we won't get the zero lift angle of attack. So because that angle also will be zero. Zero angle will be zero for the symmetrical aerofoil. But for the cambered aerofoil, for this case, and this is we are getting the zero lift angle of attack. At zero, this condition only zero lift. At this condition, the angle of attack is negative. So this negative angle of attack we are getting from the for the cambered aerofoil. So and this one, this is for whenever we say this is for the aerofoil, and this one is for the wing. This is for the wing. We can say this is for wing, and this is for aerofoil. Actually, this point is found out. This point and stalling angle, especially the stalling point, where both the points are found out by using the experimental techniques. So, because these two points are very important for defining the slope as well as defining this stalling angle. So these 2 points are important. So we have to see because moreover, whenever this point is reached, the flow will become unstable. So in the unstable condition, finding this point is very difficult. By the experimental with the proper technique, with the proper experimental techniques, we can find out both the points. So this here we see that a zero lift angle of attack, and the zero lift angle of attack for the wing and the zero lift angle of attack for the aerofoil, both are same. By taking this condition, zero lift angle of attack of the aerofoil and equal to the zero lift angle of attack of the wing. By taking this condition, we are setting up the angle of incidence in the aircraft. So angle of incidence is the fixed point, okay, with which is making the angle with respect to the longitudinal axis and to the chord length of the aerofoil. So that is we are just finding that angle will be fixed while fixing the aircraft wing into the fuselage. So that time only angle of incidence is fixed. So here, so that is the reason. So this is a condition. So moreover, we will take it as the zero lift angle of attack is the same. Means zero lift angle of attack is the same for aerofoil and wing. And another condition, another point is just we are saying that aerofoil has this CL max at a given angle of attack, the stalling angle. So this is CL max and also this CL max, both of them will be the same. So this condition, based on this condition only, by using the approximately equal to same for the CL max of the aerofoil and CL max of the wing, but it differs only in the angle of attack. Stalling angle differs for the aerofoil and wing. So for the wing, stalling angle is higher. For the aerofoil, the stalling angle is slightly lower. So this is this angle mainly because of the platform area, then we are getting the highest stalling angle, and also the flow condition over the wing and as well as the aerofoil are different. So because of that, the stalling angle increases, and then the aerofoil configuration. So that is the reason. The slope of the CL-alpha curve, this is nothing but slope of the CL-alpha curve. In the slope of the CL-alpha curve, from this curve we can see that how the slope varies. For this case, the slope will be slightly higher. For this case, slope will be slightly lower, and this case still it is still lower. It means on this slope of this is nothing but y2 minus y1 divided by x2 minus x1. So this is the slope of the curve. So for this case, as the curve becomes this straight line becomes more and more steeper, the slope also increases, and as this becomes shallow, and the slope also decreases. So this curve will have the higher slope than this curve. So that is the idea. And another thing is for the CL max already we discussed. CL max is having that means same, approximately equal to same for the aerofoil as well as wing. And in the case of symmetrical aerofoil, the CL max obviously will be less than this. So that is the reason just it is, we have shown it a little earlier, that is smaller. And this stalling angle is already we discussed. The stalling angle also will be different for the aerofoil and wing. And for the wing, the stalling angle will be slightly higher than the aerofoil. So that is based on this condition, that by having the condition that CL max is approximately equal to same for the wing and the aerofoil, we are getting this one. Generally in the equilibrium condition or steady rod flight, we used to say lift equal to weight. So it's nothing but lift, generally we say it is equal to half rho CL half rho V square S. So in this case, if I replace this into L, W, so W equal to CL into CL into half rho V square S. So for the maximum condition, because it happens in the maximum condition, maximum CL condition, so that time the lift becomes weight. So that is what. So here equal to CL becomes maximum, and the velocity becomes stalling velocity. So this is. So when the CL becomes maximum, the velocity becomes minimum. So that is the idea, that you see Vs equal to square root of 2W divided by 2W divided by rho CL max into S. So this is the condition for the stalling velocity. It means by keeping this condition and by keeping the value, the CL max approximately equal to aerofoil and wing, and just we are getting the stalling velocity is nothing but whenever the CL max increases, whenever this is the CL max, CL is the maximum at this condition. It means this is the minimum. That means stalling velocity is this is the minimum. So we can say stalling velocity because CL can be anything. If CL value is lower than this value, then this velocity will be increasing. So as the CL reaches the maximum value, the velocity will be the minimum. So we can say that stalling velocity is the lowest velocity at which the aircraft can fly in the air. So this is the minimum velocity. Below this we cannot go. If you fly below this, the aircraft cannot sustain in the air. So that is the reason we say that the stalling velocity is the lowest velocity at which the aircraft can fly. Thank you.